In this lesson, we're going to be talking about sequences, and sequences are going to lead us into our major topic for this semester, which is infinite series. So a sequence. What a sequence is, it's basically, like a better words, it's a list of numbers. So usually there's a function attached to it. So say I have a function, a sub n equals 2n minus 3. You have the first value, which is 1. So I'm plugging in 1 for n. So I get 4 minus 3. I plug in 2 but if I plug in 1, I get 2 minus 3, which is a negative 1. Woohoo! If I plug in 2, I get 4 minus 3, which is a positive 1. Third term would be 3, and so on, and you see that my sequence is negative 1, 1, 3, and so on. And you can be finite, which means we have an end, or infinite, goes on forever. We're going to be dealing with infinite series during this chapter. Okay, first to find the first 5 terms. Hopefully I will do better at this one. So if I plug in 1 for n, I get 1/2. If I plug in 2, I get 4, 5. If I plug in 3, I get 1/10. If I plug in 4, if I plug in 5, we get 1/26. I don't know why that was so hard for me. Okay, so you should have remembered this from not only Algebra 2, but also a pre-calculus class. In this case, this is a recursive. So you deal with the previous term. Okay, so they tell me my first term is 2. To get to my second term, the n plus 1 term, okay, so the 1 plus 1 term, you use the first term, which is then 6. So then my third term is 3 times the previous term, 18. The fourth term is 3 times the previous term, and the fifth term is 3 times the previous term, which is 162. Okay, convergent sequences. So a sequence converges if the limit as n goes to infinity of the function that we're talking about has some sort of limit. As you keep plugging in numbers, what number are you getting closer to, if you think about it? Okay, and it diverges if the limit as n goes to infinity of our sequence does not exist, or I can't find the limit, or it's something like infinity. Okay, so let's look at some examples. Oh, I apologize. And there's some rules here. You may want to pause the video and write them down, but I feel like the rules are fairly self-explanatory. So if you have a limit that's L, a limit that's M, you're finding a sum, you can just add the limits, difference, subtract the limits, product, we can multiply them, we can pull a constant out in front, and then we can divide the limits. I feel like those are super self-explanatory. We're not going to be doing a whole lot with the limits with these rules. I just want you guys to be aware of them. Okay, so determine the convergence or divergence of the sequence. Sequence convergence, find its limit. Okay, so you have to remember, really you have to remember your infinite limits here. Looking at this, hopefully you realize you don't have to do a lot of work, that equals 1/3. So this converges to negative 1/3. Basically, as I keep plugging numbers bigger and bigger and bigger in, we're going to converge to negative 1/3. Now, if, so this one now, limit as n goes to infinity of n squared over 11 plus 6n. Hopefully you realize that the top power is bigger than the bottom power, so this limit does not exist because it goes to infinity. So this one diverges. What am I doing? There we go. That's what I'm doing. Okay. The next example. And you can always these expressions, I'm trying to write an expression for this sequence, and everybody's can be a little bit different. But what you want to look at is this is the first term, second term, third term, fourth term, fifth term. So basically n equals 1, 2, 3, 4, 5. Try and find some relationship between those term numbers and the numbers in your sequence. That's the hardest part. And I remember struggling with these in school because I don't think I made that connection. So hopefully you're realizing that the numerator is the term number. The denominator, okay. I keep going up by 3, up by 3, up by 3. If you remember back, that's a common difference. Okay, so it's a common difference. So 3 times my term number minus 1. And you're just going to have to look for a pattern and try and play around with it. If I give you a question like this on a quiz or a test, I'm going to make it so it's not super challenging. Look for squares of numbers, cubes of numbers, and like differences in there. Okay, but again, my hint for you is going to be to always try and write this in terms of these term numbers. So try and look and see what the term numbers are. Okay, a monotonic sequence. So a monotonic sequence is monotonic when its terms are non-decreasing or when its terms are non-increasing. And I was looking at this right before I recorded the video, and I found it kind of interesting, this definition. And I'm going to go look this up in a couple different books. But where its terms are non-increasing, isn't that a fancy way of saying decreasing? Non-increasing, isn't that a fancy way of saying decreasing? I just wonder. I don't know. I might do a little bit more of research on that before we talk about this in class, but I just found that interesting that that's how our book is defining this. Anyway, okay, so determine whether each sequence given the nth term is monotonic. So you want to figure out, is this increasing? Are my terms either getting bigger or smaller? So my first one, if I plug in 1, I get 3. As I plug in 2, I get 7. As I plug in 3, I get 10. Am I doing this right? Let me see. Yes. 2, 4, this should be 5. I don't know what I was thinking. 3 times, I cannot do math. Right now, it is Christmas break, 2020, December 30th, and I just can't do math. I was struggling today doing math. 6, so now I'm at 7. My fourth term, 4 times 2 is 8, 9. Because I was looking at these. Each of these, as I'm looking at this pattern, are going up by 2. So this is a monotonic sequence, okay? And you can list out a few and notice that their pattern is going up, okay? The next one, hopefully I will do better with this one. We will see. You see how I've been struggling. If I plug in 1, I get 3 over 2. As I plug in 2, I get 6 over 5. As I plug in 3, I get 9 over 10. So if you notice, each one of these keeps going down. If I plug in 4, I get a 12 over a 17. And I'm just finding this in my calculator real quick to make sure it keeps decreasing. So yes, this one is monotonic. Okay, and lastly, our first sequence, or this is technically a version of a geometric sequence. Our first term, if I plug in 1, is a -5. If I plug in a 2, that becomes a 5. If I plug in a 3, that becomes a -5. If I plug in a 4, that becomes a 5. So notice how, because you have your -1 to a power, actually that's not a geometric sequence, sorry. If you have your -1 to a power, you just keep oscillating between -5 and 5, so this is non-monotonic. And I realized in the middle there, this is not geometric. Geometric, these would have to be going up by a certain ratio. So I was wrong when I said that that was geometric. Okay, definition of a bounded sequence. So a sequence is bounded above if there is a real number m such that our sequence is less than or equal to m, or it is bounded below if n is a number less than or equal to the sequence. A sequence is bounded when it is bounded above. A sequence is bounded when it is bounded above and bounded below. If a sequence is bounded and monotonic, then it converges. Okay, so let me relook at this. Okay, so I'm bounded above if there's some value m, okay, some real number where my sequence is always greater than m. I'm sorry, my sequence is always less than m, and a real number n such that my sequence is always greater than that number. Okay, and that is called and bounded below. And it's considered bounded when it is both bounded above and below. Okay, so let's try a few of these examples. Okay, so our first example here. Determine whether each sequence with a given nth term is monotonic and whether or not it is bounded. So as I plug in my first term, I have e to the 1 over 1. I have e squared over 8. I'm going to find some values for these. For this one, I get 2.718. Here, I get 0.924. My fourth one, I'm sorry, my third one, e to the third, 3 to the third is 27. So I do e to the third divided by 3 to the third. E to the fourth, I apologize, I didn't do these ahead of time. Ooh, I'm glad that I did this last one because I was looking at this And in my notes, I have that this is not monotonic. And I noticed that, wait, my numbers keep going down, but then when I get to e to the fourth, I start increasing again. Because if you think about this, which function is getting bigger faster? An exponential or a power function? An exponential function is going to override it. So eventually the top is going to get bigger faster. So this is not monotonic, and it is also not bounded. Because as I was looking at these numbers, okay, now I'm going to go up to infinity. So it's not monotonic and not bounded. I can't go to a certain value. Okay. Ooh, this is going to be a good example of bounding. Our first one. Okay. So I have, if I plug in 1 there, I have 2 minus 1, which is 1. If I plug in 2, I have a 2 plus 1, which is 3. If I plug in 3, if I plug in 4. So you're kind of oscillating between all these terms, and hopefully you see that pattern. Because this is going to be a -1 now, I would have a 1 if it was 6. So we are not monotonic. It is not all decreasing or increasing. But it is bounded. It is bounded because I have a number on top that it's not going to get bigger than. I have a number on the bottom it's not going to get bigger than. Okay, remember it was a number where my sequence is going to be, I'm going to look at it like this, where my sequence is going to be greater than some number, so it's greater than or equal to 1, but less than or equal to 3. Okay, so that's how I'm looking at that one. Okay, last example. If I plug in 1, I get 3 over, I'm doing these in my calculator because I'm kind of struggling today. I had anticipations of doing a lot more videos. Okay, let's look at this. Okay, so if I plug in 2, so now what I do is I plug in 2, 4, I get a 12 on the top, I get a 1 minus a 8 on the bottom, and I'm going to get that as a decimal. I actually, remind me in class, I'll show you guys how to get these values as decimals in your calculator pretty quickly. It's just a setting you need to change on your calculator that will really help you out, and you can actually see this a lot better. The third one is negative 1.588. My fourth one is negative 1.548. And they keep getting, technically it's getting larger, but the absolute value of them is getting smaller. So therefore, we are monotonic. And then let's see, is it bounded? Is there a number that it's going to be less than? Yeah, it looks like it's always going to be less than -3. Is there a number it's going to be greater than? And I was thinking about this before I recorded the video. As n goes to infinity, as I look at that function, is there something here that this is going to go to? Yeah, it looks like it's going to -3/2. Remind me to show you on your calculator how you can kind of see that by looking at a table of values. And as I keep scrolling on my table of values, I'm on like the 20th term, and it's getting closer and closer and closer. So it is bounded below by negative 3 halves. Okay, so that is your introduction and review for sequences. I hope you enjoyed our video.